Yes, take your attendance, sir.
Get it right. Like this, bro. Like.
Got 4 people.
Online. Okay, class will be starting the next topic, 14th topic, medical physics. So we have another 2 topics, 14 and 15. So this week and next week. The 14th topic going to be all your medical physics, all the scanning techniques we have in the hospital. Okay. And the last topic going to be your cosmology, astrophysics. Okay, so today we're going to start with actually there are 4 scanning. There are many scanning techniques in hospital, but the one we focus is just going to be ultrasound. Okay. Okay, so what are the scanning techniques we have in hospital? The main one, the expensive one. X-ray. X-ray is expensive. X-ray is okay, 60 ringgit for one shot. MRI. You go for MRI, how much you need to pay? You need to pay about 1,000 for one scan. Maybe for your head, you want to scan 1,000. If it's not clear, they include dye, so you have to pay another 500. So 1,500 for scanning, 300 for the doctor's report, 1 page of report.
So why so expensive? Why so expensive?
Because you know what is going on with the image.
Oh, the machine very expensive.
Yeah.
The machine very expensive.
Because the technology they need to, the technology they used, they say the machine is quite expensive. So, yeah, so MRI, after MRI, what is the compatible with MRI? CT scan. CT scan MRI is the top level of scanning nowadays. MRI developed so well until now, even the heart blockage, they're going for MRI. But best is angiogram, of course, to check any blocks, but MRI looks quite clear too. But unfortunately, you are the first batch, MRI has been removed from the syllabus. I don't know why they removed it. So you never learn about MRI, you learn about ultrasound, you learn about CT scan, you learn about X-ray. They include something new called PET scan. PET scan, injecting body with the radioactive material to find the cancer cells. That's newly added to your syllabus. Okay. So today and tomorrow we'll be talking about ultrasound. Okay, anyone been to ultrasound scanning before? No. You, ultrasound. For what?
And also the baby inside my mouth.
Oh. So still remember. So yeah, normally for the fetus development, baby development, we use ultrasound. So ultrasound scanning is ultrasonography, medical imaging technique uses high frequency sound wave. Quite safe. So more than high frequency means more than 20,000 hertz. But normally the one uses I think around 100,000 hertz of the frequency they use for the sound. Okay, because high frequency it can penetrate into the body. Okay, penetrate into the body, so can when it penetrates, it go deep to every layer, one layer to another layer, maybe soft tissue to the bone. So partially will be reflected, partially will be transmitted. The reflected beam will be used to get the image. Okay. So yeah, so high frequency sound wave is used, similar to echolocation, like based on echo reflection is used to form the image. Okay. Yeah. So of course, the main reason so far used is for the fetus development. Yeah, of course, thyroid gland detect stone in kidneys. They use ultrasound. Safe, quite safe. As I said, sound is not really damaging. Yeah. So detect stones. Yeah. So this is the like the white. Okay. Anything it should be dark. So let's say it's white. That means quite a calcinated region stone. Okay, actually, when you see the ultrasound imaging, the doctor will tell, oh, this is the kidney, this is the stone, small stone appeared here. But when you see the image, you are not really recognizing. It's a black and white actually. Okay, is it ultrasound good for the bone? Bone is bad. You can't detect bone. Okay, ultrasound useless to check any bones because of what? Bone absorbs most of the ultrasound. So we never emit, so we can't detect what is going on in the bone. So bone will look like dark. Okay, this is one image. Now quite clear. The technology improved a lot.
As a baby.
Wow. Yeah. Okay, so lots of words. Let's go for the highlighted one. Okay. So of course, looks like a computer. You have a monitor. You have a keyboard. You have something called transducer. Transducer. Transducer is one use. The main function we're going to discuss. The transducer is the one. The transducer is the one emitting. The transducer is the one emitting ultrasound and receiving back the ultrasound. Yeah, so the transducer probe that sends and receives the sound waves. Okay, the probe. The transducer pulse control changes the amplitude and frequency regulation. Not that important. Main thing is the transducer you have to know. What is transducer? Transducer is a device that producing and receiving it acts as what do you call emitter and receiver of ultrasound. Okay, the transducer. Of course, CPU processing the data and process whatever the data was recalled and display the image. Okay, and yeah, keyboards to adjust, enlarge, and shrink. Okay, everything they can done by using the keyboard. Okay. So rough sketch. Right? So transducer sent at bottom, partially reflected. The reflected beam will be sent to the CPU and sent to the display. After your doctor talks about so this is what going on to the baby, then it will store it and give you a disk. Now not anymore disk. Yeah, 10 plus to see the images. You can print some for kidney stone they will print for you. Okay, for the further when you see the doctor. Okay. Okay, our focus is about the transducer, how ultrasound is produced, what is inside, how it receives back, Okay. So transistor. Okay, transistor generates sound waves, ultrasound, by using electric potential to vibrate a crystal. Okay, it made of, there is a crystal in between the transistor. We use like a parallel plate. Okay, parallel plate, we use electric field, alternating electric field. The frequency of the electric field is equal to close to the frequency of the ultrasound. Vibrate the crystal produces the sound. Okay, so now, why crystal vibrates? What the crystal will? Okay, so what we're going to explore. So, a brief idea: transistor generates sound by oscillating a crystal inside by using a electric potential difference. Electric field is used. Okay. Yeah, the transistor send out the sound waves, pulses. Listen for echoes. I told you that, returning from the structure within the body, produce an image. Okay. The image is produced based on two factors. Okay. The time takes for the echo to receive. Okay. It takes more time to receive. That means the layer, the boundary is quite deep. So fast you receive the echo. That means the time tells how deep is the boundary. Okay. And the strength. How strong is the echo you receive? Okay. By referring to the strength, they can know the layer weight of what type of tissue. Okay. If the echo, it don't have echo at all, it made up with most probably with the bone layer. Okay. Okay. If majority bounce back, that means they know it has a gas layer. Okay. We will discuss what going to give big echo, which is small beta. So if your stomach got full of gas, I don't think so. Ultrasound going to be accurate. Majority will be reflected before get into the body. Okay. So the image produced based on what? Two factors: time, how long it takes for the echo to receive, and how strong is the echo. Okay, that's the nature of the boundary. Okay. Okay, yeah, the sound takes longer to return, will show a further away in the image, quite deep inside the boundary. Stronger sound wave will show the, stronger sound wave. Yeah, the echo is very, very intense. I mean, the image will be very bright, white, white color, white is the echo is quite strong. The dark means maybe no echo at all, no echo from that region. Okay. So very bright means shows that many has been reflected. Okay, your stomach got lots of gas. When the doctor places the transducer, you see the screen full of white, so you know a lot of gas. Okay, so yeah. So going into the transducer, so there are different types of transducers, but basically made of a crystal inside. It's a parallel plate. You apply a potential difference. This crystal called piezoelectric transducer. It's called piezoelectric crystal or piezoelectric transducer. Okay. So acoustic plate. The main thing is made of crystal, parallel plate. Okay. Okay, so again the highlighted words. So transfer probe, main part of the ultrasound machine. I told you. Yeah. Make sound waves, receive echoes. Piezoelectric transfer effect cause crystal to oscillate. And a potential is applied, the change in shape rapidly happens. So the crystal produces sound wave, and sound waves pressure waves hits the crystal, they emit electric pulse. Okay, for me to explain this, why the crystal vibrates. Okay, we go to the next slide, please. A few slides away, just to show what is crystal made of. Okay, this crystal is actually a tetrahedron shape. I go to another next slide. Okay. Yeah, it is a silicon 4 oxide. Okay, silicon 4 oxide. So the crystal is made of silicon 4 oxide. So center is silicon surrounded by 4 oxygen atoms, and it made in a tetrahedron arrangement. You learn that in chemistry, tetrahedron arrangement. So it will be a tetrahedron. So yeah, so center is silicon, 4 oxygens. So of course it's neutral, okay, but although the particle is neutral, but where lies more positive charge? where has more negative charge. The bottom region is more negatively charged, 3 oxygen at the bottom. So total is neutral, but more negative at the bottom. Okay, positive is little higher. Okay, so down region is more negative than upper region, little positive. Okay. So yeah, so the quartz is made of a large number of repeating tetrahedral units, silicon oxide. The position of oxygen links are not rigidly fixed. Oxygen is negatively charged. Movement can be encouraged by applying an electric field. Okay, because silicon, oxygen all are charged individually. So you apply an electric field. If upper plate is positive, the silicon will move down. The oxygen will move up. Okay, they try to move up. Of course, they cannot completely move up. But what will happen? When the silicon moves down, the oxygen moves up. So the crystal like compressed. Kind of compression happens, a little compression happens. Okay? So when up is positive, down is negative. Okay? You apply electric field. Okay? You change the polarity, then what happens? Silicon will move up, oxygen will move down, so the crystal will expand. Okay? Can imagine? So if you have a high frequency, the crystal start to oscillate, and resonance happens, you give out ultrasound. Okay? So yeah, this is what I told you. So when you apply electric field of negative, down is positive, the silicon will move up, the oxygen will move up, the crystal little expanded, and the other way around, compressed. When the crystal is unstressed, so unstressed, no electric field is applied. The positive negative ions are bound to lattice in the nucleus. Their effects are neutralized. Okay. If a constant voltage is applied, the positive silicon ion attracted towards the cathode, the negative oxygen towards the anode. This causes distortion of silicate units, movement of silicate units, depending to the polarity of the voltage. The crystal becomes either thinner or thicker. These are altered charge distribution. So, to be one word, you can say the crystal tend to oscillate and electric field is applied. Okay, electric field is applied. So the grading voltage set up for mechanical vibration. Okay. The frequency of applied voltage same as the natural frequency of the crystal. Resonance happens, produces ultrasound. Okay, produce sound. Okay. Sound which we can't sense it, of course. It's ultrasound. High frequency we can't sense. Okay. Okay. So this is how transducer produces ultrasound. Okay. So we apply a voltage to the electric field, allow the crystal to oscillate. So when the frequency of the voltage matches the natural frequency of the crystal, ultrasound produces. Okay, the natural frequency of the crystal is found to be in the ultrasound region. Okay, so we use this particular crystal. Okay, so get ultrasound. Okay. Okay, ultrasonic transfer can be used as a risk. Okay, now this first we talk about producing ultrasound. Okay, produce ultrasound transmitted to the body. Now the echo will receive back to the transducer. So now the transducer is going to act as a receiver, receiving the ultrasound. So how you can receive the ultrasound, you can detect. Okay. So now once they send the pulse by electric field, they shut down the electric field. Okay, wait for the echo to receive back. Okay, when the echo receive back, no voltage is applied. Okay, no voltage applied to the electric field. You never apply electric field to the no external voltage is applied. And the echo receive, what happened? The other way around. Ultrasonic transfer can be also as a receiver. When an ultrasonic wave is incident on unstressed piezoelectric transistor, the pressure variation alter the position of the crystal. Now the sound which is reflected will go and oscillate the crystal. Okay, the sound, ultrasound will come back, going to oscillate the crystal. Okay, so now crystal oscillating, what happened? When silicon goes up, upper plate will be a little like positive, down plate will become little negative, so it produces a small voltage. develop. Okay, so receiving, changing the sound wave to electrical signal. Okay, so when receiving, so the pressure variation alter the position of the ion crystal. This induces opposite charges, producing a potential difference. Made. These varying potentials can be amplified and processed to form the image. Okay. So the other way around. Okay. So first, voltage electric field is used to produce the ultrasound. Later, the sound vibrate the crystal, produce the potential difference band. Okay. The potential difference will be amplified and processed to form the image. How deep is the layer? Okay. Okay, so as I told you, this is what so partially reflected, partially transmitted the ultrasound. So the imaging performed by emitting a pulse, partly reflected, partially transmitted. The reflection depends on the something difference in impedance of the tissue. Okay. So what is impedance? So how much will be reflected, how much is transmitted, depends to some quality, special quality for the tissue called impedance, or more to say called acoustic impedance. Depend to the acoustic impedance value of the tissue. Okay, what is acoustic impedance? Reflected, transmitted. It's all the same story. Time taken depends on the distance, amplitude, energy being reflected. So this is the same story. The time tells how deep is the boundary, and the amplitude tells the nature of the boundary. Okay. Okay. I just go to the acoustic impedance first. Skip this. Okay. So the beam which is transmitted, partially will be reflected, partially will be transmitted. So of course, intensity formula, the I is IR plus IT, right? Okay. Okay, we go to the next one. The acoustic impedance, which determines how much is reflected, how much is transmitted. First of all, what is meant by acoustic impedance of the medium? A new quality, something new, never learned, medical and medical. So acoustic impedance is said to be is a product of the density of the tissue and the speed of sound in that tissue. It's called acoustic impedance. So what is acoustic impedance? It's the product of the density of the tissue and the speed of sound in that tissue. Okay, it's called acoustic impedance. Like half-life definition, K constant definition, or ultrasound famous definition. What is meant by acoustic impedance? It's a product of density of the tissue and the speed of sound travel in that tissue. Okay. Okay, so this acoustic impedance determines how much reflects. Okay. So under medical, they found that IROI, the IR is what? The reflected intensity over the incident intensity. Reflected over the incident. The IROI, they say, for the two medium, okay, first medium, second medium, is related to this formula. Okay. So this formula is all full of the acoustic impedance value. Okay. So this alpha called intensity reflection coefficient is alpha. Okay. IROI, alpha is IROI. If alpha big means majority will be, if alpha big means majority will be reflected or transmitted. If alpha big means reflected. So if alpha big means majority will be reflected. Okay. is the intensity reflection coefficient of two boundaries. And this for two boundaries, two medium, the border of two mediums. Let's say soft tissue and bone. Okay, soft tissue and bone. The intensity reflection coefficient for that boundary is alpha. Let's say 0.9. Let's say alpha is 0.9. So you should know from tissue to the bone when the ultrasound hit, 90% will be reflected. Okay, so alpha is 0.9. Okay. So it all depends on the acoustic impedance of that two medium. Soft tissue Z1, bone is Z2. So this is common. Now tell me, alpha is huge. Okay, from this formula, you can predict. Alpha is huge. Majority will be reflected, and the acoustic impedance of the both medium is about the same or big difference. Big difference, majority will be reflected. Alpha is huge, isn't it? Alpha is huge, and the Z2, Z1 big difference. Okay? Yeah, big difference means the what? Numerator. Numerator get big, Z2 minus Z1 get big, right? So therefore, alpha of chance to get greater. Okay? So conclusion is what? Two medium have a very big difference in acoustic impedance. So the ultrasound majority will be reflected. Just reflect. Never go in. You only penetrate and the acoustic impedance of both tissues is about the same. About the same only it will penetrate. Okay? Big difference, it will reflect majority. Okay? That's what has been found so far in medical and the ultrasound. Okay? The intensity reflection coefficient tells you how much it is reflected and how much the acoustic the intensity reflection coefficient depend to the acoustic impedance of the two medium. Okay? If it has a big difference, majority will be reflected. Okay? So this formula so far in exam, keep providing this formula. So looks like you don't need to memorize, but don't trust Cambridge, it's better remember. Okay. Okay. Technical term. So what is acoustic impedance? It's the product of density and the speed of sound in that medium. Acoustic impedance determines the reflection coefficient. Okay. Okay. So from here we're going to move on. You need to know this well. Okay, you got all the acoustic impedance of different medium. So all the water has the lowest, bone has quite a huge acoustic impedance, very dense. Very dense. Speed of sound also quite. Speed of sound travel faster in the more dense medium, right? Yeah. So yeah. So bone has a very huge acoustic impedance. Water very low. Blood still quite high, 1.5. So this speed of the sound is that different medium. All this information will be provided when they ask questions. This is the absorption coefficient. 120. No, this is I haven't seen here. This is absorption. We will not talk about absorption. Only reflection. Absorption later. This table later. Okay. Absorption later. Okay. We just first talk about reflection. Okay. Okay. So one example. So use the data in the table. Calculate. What is the reflection coefficient for air and soft tissue? Okay. So what is the alpha of air and soft tissue? So first Z1 is air, Z2 is Z1 is soft tissue, second doesn't matter. So if you put any value also your value will be the same. So one of them Z1, another one is Z2, the key. So it will be 0.999. So conclusion is what? Majority will be reflected. Right? How many percent? 99.9% of the ultrasound intensity will be reflected. and the ultrasound travel from air to the soft tissue. Air to the soft tissue. Okay? So that's why the doctor got lots of problems sending the ultrasound from the soft tissue to the input transducer. There is a small layer of air between the transducer and the soft tissue. So antigen will be reflected. Pointless. So what they'll do, they'll try to create a medium between the transducer and the soft tissue. They try to create a medium so that that medium has the same acoustic impedance as the your skin. Okay? So that's why when you go for ultrasound, they put some sort of gel. Put a gel, they put a transducer on top of the gel. Okay? The gel will have the same acoustic impedance as your skin. So majority of ultrasound will transmit into the skin. The alpha become very small between the gel and the skin. Okay? Here looks like majority. Okay, muscle and bone. In muscle and bone, so you get 34.3 is reflected, 60% transmit into the bone, but the bone will absorb all of them. Okay, absorb all the ultrasound. Okay, like a black hole that disappears. Okay, absorption we'll talk later. First reflection. Okay, any questions so far? So just key in on the values only. Okay, another one question. So, such is why although the speed of ultrasound in blood and muscle is approximately the same, the acoustic impedance is different. Of course, the density is different, that's why acoustic impedance is different. Okay, although speed is the same. So, the density is different. So, B, complete the intensity reflection for parallel beam ultrasound boundary beam. So, same idea. Fat and muscle, what is the alpha value? Just in the two acoustic impedance for the fat and muscle. So 9.4 times 10 power 93. So what's your conclusion? Majority will be reflected or transmitted? Transmitted. Okay, this one is a lot transmitted. So in ultrasound from fat to muscle, easy. Fat to muscle, majority will go into the muscle. Okay, ultrasound. Okay. This is why I told you they use gel as a coupling medium. Contact with the skin, the gel acting as a coupling medium. So the gel will have the same acoustic impedance as the skin. So that majority transmitted first. We expect the ultrasound transmit into first. We don't want to investigate on top of skin, inside the body, what is happening. So majority need to be transmitted. So it's like a bridge on the gel. Okay. Allow the ultrasound to get in. Okay. Coupling. So nobody has been to ultrasound scanning before, Very young. Maybe age of 35. You will know in depth about ultrasound. The kidney stones, so drink lots of water. Okay, lack of water, you will suffer with the kidney stones. So, CT scan. I've been on CT scan, brain.
No, I think I've done because I need to go before surgery.
Oh, inject with time?
Yeah.
Oh,
That
terrible.
would be good.
The CT scan, one problem, they will inject with dye. The dye is one big problem.
They call it a contrast.
Yeah, contrast. You had any allergy?
Yes.
How long?
I got it the day before the surgery. They had to change my IV drip because I got an allergic reaction.
Oh, allergy. How long the allergy last?
Couple of days.
Couple of days. I went for CT scan. They get me the dye for my brain. Then body becomes so hot. After that, 1 year I got allergy. Suffered with allergy. 1 year. Yeah. So I got rashes everywhere. But in my class also I'll be scratching. 1 year. So different body, different immune system. Yeah. Ultrasound quite safe, not really allergic, just sound. Okay, so that's about reflection. So wave will be reflected. Okay, that's good. We want some wave to be reflected so that helps the scanning. Okay, to get the image. Okay. Do we want some to transmit also? We want some to transmit, right? So that it go deep and get more information. So we want partially reflected, partially still to be transmitted. So it gets go deep. Yeah. But in the transmission process, some problem happens. What happens? Of course, absorption will happen. Okay. All tissue and wave travel absorb. The tissue will absorb some energy. Yeah. So absorption, is it contribute to the imaging? No, we never contribute to the imaging, right? We never reflect, we never transmit also, it just absorbs like a black hole. So it's damage to the imaging one. We can't do anything because some tissue really like to absorb ultrasound. Okay? So we're going to talk about, study about absorption. Okay? How much it will absorb? How much the transmitted intensity will be. Okay? So this is the idea. So the initial intensity is I0 when passed through a tissue of a thickness of X, and when it transmitted is the remaining intensity transmitted. Okay. The I and I0 is how they related. They found that this equation relates the intensity output and the input. Okay. Exactly same as the what formula? Half-life formula. Exactly like half-life concept, right? N equals to N naught E negative lambda T. Okay. So the intensity drops exponentially. Okay. With thickness. This case is thickness. More greater the thickness, the intensity drops exponentially. Okay. Not in terms of time. This one is thickness. Greater thickness, more lower the I. Greater K. K is called absorption coefficient. It depends on the tissue, the type of tissue. Okay. The earlier, the table I show you, one table I said skip first to give that absorption coefficient, right? This is the absorption coefficient. How much capability to absorb? So bone 130, what is 130? Muscle are not very low, but bone a lot 130. Okay. Absorption coefficient. So you have two coefficients, reflection coefficient and absorption coefficient. Okay, we go back. This absorption coefficient depends to two factors. One is the type of tissue. Another factor affects is the frequency of the sound transmitted. Okay, higher the frequency, greater the absorption. Okay, greater the absorption. Higher the frequency sound is sent. Okay. So K actually depends on two factors. Depend on the frequency of the ultrasound and the type of tissue. Okay. Okay. Okay, so let's be. This is the ultimate calculation question for under medical. Under medical, this is one of the tricky one. Okay. So this question, what they're going to ask is, the ultrasound sent in on the skin. Okay. So let me draw. Wait, what? Okay. So see here, let's say this is your skin here. Skin. Let's say this is your bone. This is your bone layer. This is a bone. Okay, this muscle here, muscle. Muscle bone. Okay. So when the ultrasound emerged inside the skin, let's say with the intensity of I0. Okay, I0 go to the muscle and reaches the muscle, then reflected, reach the skin. Okay. So this is I0 and reach here is I1 then reflected I2 reach at the surface I3, different intensity, right? I0 is the original intensity, and go reach the muscle at I1. I1 intensity is lower than I0. What happened from I0 to I1? What process happened? Absorption happened. Okay, absorption causes I1 to be lower than I0, right? Absorption happens, no reflection yet. Reflection only happens at the boundary. So I0 become I1, then I1 tend to become I2 because of what? Because of partially reflected. I1, I2 lower than I1. Then I2 to I3 again, absorption happened. Okay. The next exam they will ask, what is the ratio of I3 to I0? What is the ratio of I3 to I0? Okay. This question they will ask very common under ultrasound. So what the question? What is the value of I3 over I0? How much? What is the fraction? Okay. Okay. So how do you do this? Okay. So let me teach you. I3 connect to I0 is quite far away. Got absorption, got reflection, got absorption. Okay. Then only I0 relate to I3. So we need to get a formula I3 relate to I0, but not direct. Can you form a formula for I0 relate to I1 first? How I0 relate to I1? I0 relate to I1, we can form an equation, right? Anyone? I0, I1. What formula? Absorption or reflection? Absorption. So how I1, I0 related? I1 equals to I0 E negative Kx, right? Kx, X is the thickness, right? Okay. First formula. Okay. So this is how I1 and I0 related, right? I1 is absorption, so I0 E negative Kx. K is the absorption coefficient of this medium. X is the thickness. Okay. We want to get what? We want to get how I3 connect to I0 to get the fraction. Okay, first formula. Can you get the second formula now? How I1 connected to I2? How I1 connected to I2? So it's a reflection coefficient, right? So how? I2 over I1 is the reflection coefficient, alpha, correct? I2 over I1 is your reflection coefficient of which medium? Okay, muscle and bone. I put muscle and bone reflection coefficient. Correct? I2 over I1 is your reflection coefficient of the muscle and bone. So this is the second equation. Okay. Right. So now can you get third equation? I2 connect to I3. So absorption again, right? So how? I3 equals to I2 E negative K X again.
Sorry. Let the bone absorb some also, right?
Bone absorb some, but that's for the transmitted one, right? The partial will be transmitted, the transmitted will be absorbed. Okay, so actually, what we want to see, what is the intensity of this level? Of course, some transmitted, but that transmitted is another story, no, right? Okay, this is your maths knowledge. Can you combine these three so that you get I3 and I0 in a formula? Maths. Right. I3, I2, you can substitute. All right. I1 times alpha. Then I1 you can substitute in terms of I0, right? So can you get I3 and I0 in a formula? 2 minutes for you, come on. Very important. You know this, so you can do the question, ultrasound question. Okay, so I think you got the formula. So I3 equals to the I2 is substitute lah. I2 is actually what? By using the third equation, from the third equation, right? I0 is I2 is substitute as I1 alpha, mass and the muscle and the bone, E negative Kx, right? So I3, I1 already. Yeah. Then what do you do? Then from the above equation, I0, the I1 we substitute. I1 is what? I1 is I0 E negative Kx. So I1 will be I0 E negative Kx alpha B E negative Kx. Yeah. Okay, this right. Okay. So we successfully get the, this is I3. I3 I0, right? So we got I3 I0 already. So I3 I0. This is what? This is your absorption. Absorption. This is what? This is your reflection. This is what? This is your absorption again. Okay, absorption. Okay. So whenever it does absorption, E negative Kx. Okay. Whenever you do reflection, multiply by alpha. Okay. Absorb again, E negative Kx. Okay. Whenever absorption, E negative Kx. Shortcut. So this can be combined, become what? E negative Kx become E negative 2 Kx, right? Your indices, the power become added. So alpha, yeah. So this is the final formula, right? So this formula can give us the ratio of I3 over I0. Yeah, I3 over T. Actually form this 3. Yeah. Okay, so I3 over I0 ratio is this one. K is the absorption coefficient, X is the thickness of the layer, alpha is the reflection coefficient of this boundary. Okay. So you don't need to know these 3 also. Just remember this. And absorption, E negative Kx to be used. For reflection, alpha need to be multiplied. For another absorption, E negative Kx to be used. Let's see how well you got this idea. Okay, if you know this, you can proceed any reflection. Okay, let me see how well you adapt to this formula. Can we go to another one? Another one. Okay. So I skip this first. Okay, I move up. Okay, I give you a little complex one. You have first layer, second layer, and the third layer. Yeah. This is medium 1, medium 2. This is medium 3 at the bottom. Okay. So this is whatever 1, 2 is alpha 1, 2. Whatever 2, 3, alpha 2, 3. Okay. Alpha 2, 3. Absorption coefficient first medium, I just put K1. K1. This is your K2. Okay. Okay. Now question is, okay, want to find, this is the I0, goes into the body here, then partially reflected, goes into this body, then reflected. Okay, let's say, I just want to see here. Just checking. This is I final I. Okay. So I0 here will be I1. The reflected will be I2, right? But transmitted is I3. Then here I4. Then reflected I5. Then this is I6. Okay. So I0, I3 after absorption I1. Partially reflected I2. Partially transmitted I3. Absorb again I4. Partially reflected I5. Absorb again I6. Okay. The question is, can you find the ratio of I6 to I0? I6 to I0. Come on. You can do this. Absorption E negative Kx. Reflection alpha multiply. You can get the ratio. See how many times is reflected, how many times absorbed. But here I2 is useless, right? It's not going for I2. I0 to I1, oh, we go I0 to I6, We are asking I6 equals to I0. What are the things need to be added here? How many absorption? I0, I6 to I0? 1, 2, 3 absorptions.
So the option is I1 to I3.
Okay. Here is a reflection or transmission. This is now multiplied by alpha, right? Multiply by alpha for the reflection beam, right? Right? This one, do you take the reflection or the transmitted one? You need to take the transmitted one. So transmitted one, you multiply by, do you multiply by alpha? If you multiply by alpha, you get the I2. So you multiply by what? Alpha is what? Is fraction, reflection coefficient, right? Okay. If this is alpha, this will be 1 minus alpha. If alpha is 0.6, then it means what? 60% reflected. That means how many transmitted? 40% transmitted. 0.6 alpha means this should be 0.4, right? So what do you have to do? You get the I3, you multiply by what? 1 minus alpha. Transmitted 1 minus alpha. Reflected alpha. Okay. Absorb, 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 reabsorb. 1 transmitted, 1 minus alpha. 1 reflected, multiplied by alpha. Right? So what's the formula going to be? So the formula should be, the first one is I0 E negative K X, the K is K1, okay, this is the one first medium, multiply by, to go to I3, I must do 1 minus alpha, alpha what? Alpha of 1, 2, okay, this is transmitted, okay, this is transmitted, then multiply by the second absorption E3 to E4, E negative K2 X, let's say this thickness also, both this X, this also X, multiply by E4 to E5 also reflected, right? So multiply by alpha what? Alpha of 2, 3, then more multiplication. Multiply by E negative third absorption, negative K2 X. What you should get? Alpha or 2, absorption E, reflected alpha, transmitted 1 minus alpha. Okay, just multiply when you get the beginning to the end intensity link. Okay. Yes, think about this, time's up. Okay, so we'll be continuing this tomorrow after your design expense. Okay, so we stop it.